Okay, folks, we're almost ready to get started again. Hopefully, I'm not sure if there's any newcomers who weren't here for the first half of this morning's tutorial, but we're kind of dealing with some logistical challenges in that Steve Wallace, who was the guy to present this morning, had some problems with his flight getting delayed and missing connection and so forth. So he's not able to physically be here and present, but he is going to present using Skype and what the so just a reminder that let me go back to the sign-in slide is up there, and that's a roster where it's a Google Docs spreadsheet. You needn't use your real name if you don't want to, but it's getting a little feedback there. I don't know. So the roster is a place where you can sign up for a virtual machine number and get and then the slides are ones that you can follow through. Let's see. Oh, he's rebooting Skype. All right. Let's just.
The person whom you're trying to reach is currently unavailable.
There's a British person in there. Okay, so we'll have Steve back on the line in just a minute. And back to the other. And just to remind people of how to get into to log into their VM, it's like that, where the X is the line, the row number in the spreadsheet, the Google Docs spreadsheet that you used to sign in. And there's the credentials. And if I recall correctly from the last time this was presented, that the URL there at the bottom is actually different information than what you'll find through SSH. So it's useful to look at both. So Steve just texted me that he's now rebooting his laptop, so we'll bear with him for a minute or two. And again, the VMs are let's see, where's that slide? The VMs are use Amazon Web Services. They're hosted there, and then we've got a tool called MiniNet, which is a virtual network environment. Basically, we'll set it all up. It's pretty incredibly slick when you do it. And then these other softwares, the Wireshark. Yeah, if I recall correctly, the web interface is the web interface to the Wireshark piece, and so that you can, after you configure things on the command line, you can actually observe the OpenFlow transactions and stuff going on. So hopefully you guys are able to get into those. Let's go back to that logistics one again. And hopefully we'll hear back from Steve in a minute. So thanks for bearing with us. Maybe we can quickly review the OpenFlow's value proposition. No, just kidding. Let's see. I think we're probably around slide 40 odd. Right, okay, so we're not there yet. Wait, am I going in the right direction? No. So for those of you just coming in, oh, here we go. Hello.
Hey.
Cool.
Hang on I'm restarting all my apps, so hang on 1 second.
Yep. I think all we'll need is the web browser, probably.
Yeah, I'm getting there.
Yep.
Sorry about that. I turned my Bluetooth on and it locked Skype up, and then I couldn't actually reboot it. I'd like force it to. Okay, NANOG 58. Presentation. Slide 40 something. Come on. Slide 48. Share screen.
Yeah, we see it. Okay.
Okay, okay, cool.
And I've just got a couple other things to take care of. So Ed Bayless is, I don't know if you saw, you probably didn't get a chance to see my IM before you rebooted Skype, but Ed Bayless, whom I know you know, is going to sit in as, you know, in the same kind of function that I had to just see if anyone has questions from the room. And
Fantastic.
What?
Fantastic.
Okay, fantastic. Good. Okay, so I think we're ready to hand it over to you guys. Go ahead, Steve.
Okay, Ed.
Yes.
We're on slide 48.
Yeah, he can see it.
Oh, and you can see this. You can see the slides now. Never mind.
Yeah.
Yep.
Yeah, slides look good.
Okay, so everyone who wants to participate in the hands-on at this point should at least have their web browser pointed at the Amazon Web Services instance, and you should see a desktop with Wireshark and a couple terminal sessions. And those of you who want to more easily do stuff, you might get a couple SSH windows into the same host. Username, OpenFlow, password OpenFlow. So we'll be using Mininet to simulate the switches and hosts in the network we're going to do exercises on. Mininet uses OpenSwitch as its switch and creates Linux containers for each of the hosts it emulates. Once started, Mininet will give you a prompt in the shell, just Mininet greater than sign. And the next slide. Okay, so this is the first command we're going to run. We're going to start Mininet off, and we're going to build this topology with a pretty simple use of Mininet. So in one of the terminal windows, you should be able to type this command as it is on the slide, sudo space mn for Mininet space --mac space --switch space obsk space --controller space remote. You should be able to copy and paste that from the slide. You got the slides open on your desktop. And once that command executes, it will create the topology you see on the slide. So everybody should run that, and then maybe raise your hands so that Ed knows that this apparently worked.
I see lots of hands being raised.
Most excellent. Okay, a little bit about this topology. It creates two hosts, H1 and H2. It creates a switch with two Ethernet interfaces, E1 and E2. And then it creates something special on the switch. It's sort of a named pipe. We have to, the default port for OpenFlow is 6633. And for reasons that are too difficult to explain, we actually have to use the named pipe in this exercise. Okay. So we're actually going to go do something useful right off the bat. So you need to go into your web browser and maneuver yourself to the Wireshark menu. and you want to tell Wireshark to capture on the LO interface. And then once you do that, there is a field, wish I could point to it, but it's in the sort of the upper part of the Wireshark menu where you can type in a filter, and you want to type in OF without the quotes in the Wireshark filter. And what this is going to let you do, it's going to let you capture and inspect the OpenFlow protocol packets that will flow between the switch created in Mininet and the OpenFlow controller that you'll start to use in a bit. So when folks have done that part, they might raise their hand so we know we can move on.
We've got a fair number of hands.
Okay. Okay, one of the utilities we're going to use is something called OBS OFCTL. This is one of the set of things packaged with Open vSwitch. This command is actually useful regardless of whether you're using Open vSwitch. So if you were using a real HP switch, this is a useful command to have available. It's a command line utility that talks the OpenFlow protocol, and this would be one of the utilities someone might use to debug something. So you've got the switch being controlled by the controller, but let's say you want to kind of go in and poke around and see what OpenFlow stuff is being configured in the switch. Normally this would talk TCP, but like I said, in this test case, we're going to use it via the DP0 device. Okay, so now if you got Wireshark up and running, in run of your terminal windows, type this command, superuser do obs-showupctl space show space dp0, and you get to see some basic stuff. So what this command is doing, it's connecting to the switch in Mininet, and it's doing the basic show stuff, so show basic stuff, and it's doing this over the OpenFlow protocol. So do people see stuff spitting out of the command? Head with that cough mean a yes?
Yeah, well, that's a raise your hands if you guys are seeing everything cool. All right, yeah, we got a good number of hands there.
Good. Normally, I'd be walking around you guys while doing this and making sure, but can't do that. Okay, so the next interesting command is superuser do obs OFCTL dump flows dp0, and this will show any flows in the flow table that have been installed in the switch, and there should be pretty much 0. When you ran the show command, the kind of stuff you got back were things like the number and type of Ethernet devices and their Ethernet addresses, some stats about what the switch is capable of, that kind of stuff. When you run dump flows, it tells you about the flows installed in the switch, the rule itself, in other words, what the match is, the timeouts. Remember, you can have idle or hard timeouts. The actions, okay, if it matches this rule, what does the switch do with the packet? And then it also shows you packets and bytes processed by that rule. So you can look at counters and you can tell if packets are matching a certain flow rule because you'll see its counters increment. So this is a sample of what that output looks like. Pretty simple. Okay. Another one to run is dump ports. Gives you a little more detail on the ports. If you're looking for something that's equivalent to show interface, kind of, on a router, you can run OBS OFCTL dump ports. One of the things to keep in mind, because this is a real protocol, not a scripting language, if you wanted to write an application that got port statistics, you might use SNMP with a router or a switch, or you might do something like use a script that talks with CLI. On an OpenFlow device, you can use the OpenFlow protocol to get this data out, and that can be useful. You can also remove flows using OVS OFCTL. Pretty straightforward. We probably won't use that today. Okay, so next major thing in the exercise. So you should have your Wireshark capturing on the loopback with the OpenFlow filter installed, and you should have a Mininet prompt in the terminal window you use to build the topology. And so the first thing I want you to do is ping host 3 from host 2, and the syntax to do that is simply you type h2, which means run this on the host 2 instance, ping the command, and the argument to ping is h3. And just so you know, host 2 and host 3 are actually connected to an Ethernet switch. It's an OpenFlow switch, so one would think maybe you could ping each other. So go ahead and try that and see what happens.
What's the filter?
The filter on Wireshark is just using the lowercase o, f as an OpenFlow, and that will cause Wireshark to ignore everything but the OpenFlow protocol, which will get interesting in the next step of the exercise. So has everybody done the pings?
I see heads nodding.
And did they work?
No. Lots of no's.
No. Excellent, excellent. They shouldn't work because the the switch is in OpenFlow mode. Right now, the switch probably about every 10 seconds is trying to connect to an OpenFlow controller, and you don't have one running. So it's not connecting to an OpenFlow controller, and no rules are being installed in its flow table. Okay, we're going to start up an OpenFlow controller. So in a different terminal window from the Mininet window, you want to start something called OVS controller. And the command is superuser do, running a superuser OVS-controller space PTCP : it means use the default port and listen on the default interface. Default port is 6633. Go ahead and put an ampersand on that, put it in the background just to preserve your ability to use that terminal window for future stuff. Once you execute that command, there'll be a new process running on the VM. It will be listening on TCP port 6633, and that switch is within 10 seconds or so will connect to that process, and that should cause a couple things to happen. One is in the Wireshark window, you should see a bunch of Wireshark OpenFlow salad start to populate its display. And what you're seeing there is sort of the initial conversation between a controller and a switch. And you should try the pings again and look at what you see in the Wireshark display and see if the pings work. Are the pings working? Is the Wireshark display filling up with Wireshark salad?
Yes. Yeah, we're starting to see some heads bob. It's like more bobbing now. Yes, I'll go with yes.
Okay, so we're gonna spend about 10 minutes looking at this, and So let me lay out what the goal is, and you guys are going to work on this on your own for probably about 10 minutes. So this Ethernet switch, since it's running in OpenFlow mode, doesn't know how to be a conventional Ethernet switch. So all of the rules that cause it to behave consistent with the normal Ethernet switch actually have to be installed. And you want to have it, and so when you run OBS controller, its default application is to make every switch that connects to it behave like a normal Ethernet learning switch. And it also has some optimizations built in. It wants to try and keep the table size relatively small in the switch, and so it has pretty quick timeouts for some of its entries. So you get to watch, what you're watching is a reactive OpenFlow application, because what's happening is a packet comes into the switch, and if it doesn't match a flow, it's being sent to the controller. So the controller is reacting new kinds of traffic, and then it installs a rule on the switch, and then it tells the switch, here's, go ahead and process the packet again. If you go to the next slide, you can run the dump flows command again, and you can see exactly what it's installing in the switch. So here's the exercise I want you guys to do for 10 minutes, and that is, this is the first example of a pretty complete OpenFlow application. The application is to make the switch behave like a conventional learning switch. And you get to see it step by step. And so what I'm going to encourage you to do for the next 10 minutes is start at the top of the Wireshark trace where the switch connected to the controller, and go ahead and there's a little diamond that indicates that there's more detail that you can expand, and the OpenFlow dissector does a reasonably good job of providing human readable junk for you to look at. But look at what it takes during the initial negotiation with the switch, and then what you're going to see beyond that. You're going to see a couple things. One is there's this echo request that goes back and forth. This is just a mechanism for the controller and the switch to ensure that they're still connected. And then the other thing that's going to happen is you're going to see packet ends. Packet ends are when the switch sends a packet to the controller because it doesn't know what to do with it. And then you're going to see the switch send out flow modifications. Flow modifications are the switch actually putting rules in the controller putting rules in the switch to handle these packets in a way that would be consistent with the learning switch. And if you look at the dump flow output, this command that's on the screen, you'll see the flows that it's installing. They probably have fairly short timeouts, so if you stop the ping for a while, they'll probably go away, and you can start it again. So if you want to understand, a little bit, sort of the process to forward a packet through an OpenFlow switch and the communications between the controller and the switch. And the other thing that I want to point out is, so you have this virtual switch that's connecting to the controller. We've also set up on this switch an ability for you to interrogate the switch using the command line interface OBS OFCTL. This is exactly how you would debug something. So if you were deploying this for real, you'd have an application running on the controller, and the switch would connect to the controller. And if the application was behaving oddly, you would do these two things which we're doing now. You would put a sniffer between the controller and the switch to watch the OpenFlow conversation, and then you would be using a command line utility like OBS OFCTL to then interrogate the switch and see if the rules in the switch matched what was going on in the OpenFlow conversation. So now that I said all that, take 10 minutes and go through that Wireshark trace, do some extra pings, look at the dump flows, look at the stats increasing on the dump flows as you do the pings, do your best to start to get comfortable with the things that are going on for this just to behave as a regular switch. Does that make sense? Lots of nodding, Ed.
Yep, we got nodding. Sorry. Hey, Steve.
Yep.
There was a question about if you could show the link to the Google Doc, the URL for that.
Oh,
I don't know if you can bring that up somehow real quick. I don't have it on hand.
can you see it?
I think you were looking for the slides, yes? Okay.
So it's tinyurl.com/nanog58-slides.
Good. Okay, we're good to go. Thanks, Steve.
It would also take questions. Anybody has any questions?
Looks like we got a question coming up, Steve.
On the guacamole application or whatever, how do we get Wireshark to start over again? I kind of killed it.
I heard it was a question about guacamole, but I didn't hear the whole question.
He said that Wireshark needs to be restarted, or has died on it. So how do we restart is the question.
If you, in one of the command line windows, it should be, if you type sudo space Wireshark, I think it'll come up.
Would it be in would it be in the bash history somewhere too?
Probably.
Yeah. Hold on, I'll see if I can help. Yeah, okay. Steve, it's when they try to restart it, it's saying can't open display as ORGAT. So I'll take a look, but
Okay.
Steve, this is Jim Warner from UC Santa Cruz. My question is, I killed the ping, so I expected it to stop rolling by in the Wireshark window, but it still is ticking off every 5 seconds. I see an echo and a reply. And the OF filter is on.
So the switch in the OpenFlow controller continuously have this echo chatter, so it's not. I think you're not seeing an ICMP echo because you're not actually sniffing the channel that has your ping packets. What you're seeing is something labeled an echo that's part of the OpenFlow protocol, and that is simply it's to make sure that the switch and the controller have a little bit more immediate notice rather than the TCP level awareness that they lost connectivity. Hopefully that made sense. So we'll let you guys play with this for about 4 more minutes, and then we'll move on. Okay. I assume that folks are about ready to move on. So a couple of things just to kind of help this sink in. You created a network using Mininet. The switch in this network that you created was told to be an OpenFlow switch and to try to connect to a controller. You went ahead and tried to ping hosts that were interconnected via that switch before the switch could connect to a controller, and the pings failed, which is expected. You then started up a controller, a real simple controller, whose default behavior is to cause any switch that connects to it to behave pretty much like a learning switch. And then at the same time, you had your Wireshark situated so it was sniffing the control traffic from the controller to the switch, not the traffic between the host and the switch. And so what you saw was the switch attempting to connect to the controller, establishing a TCP connection to the controller and the switch having a short dialogue, exchanging some basic information. And then when you started the pings, here's what happened at a packet by packet level, or what you should have seen. So when host 2 starts to ping host 3, the first thing that host 2 is going to do is going to send out an ARP request as a broadcast, saying what is the MAC address of host 3. And that ARP request is going to hit the switch, and the switch has no rules in it. And so the default behavior for an OpenFlow 1.0 switch is when a packet comes in for which there is no match, it sends that packet to the controller. The controller will then look at the packet and decide what rules it needs to put in the switch. And at that point, you would have seen evidence in the Wireshark trace that the controller did a flow mod to the switch to put a rule in the switch for handling that ARP broadcast. Then the controller would have sent the packet back to the switch. At that point, the switch would have a rule in it that would forward that broadcast as a learning switch would. So then the ARP goes out, and you see host free will send a unicast reply, right, because it's got the MAC address from the source MAC address in the ARP packet, and it knows it's the IP address that the ARP is looking for. So it forms up an Ethernet packet, a unicast Ethernet packet, to go back to host 2, saying this is my MAC address, and it sends that packet on the wire. And again, there's no rule in the switch. So now you have a unicast ARP packet, Ethernet packet, going to the switch, and it's not going to match any rule in the switch. So that gets sent to the controller, and the controller again does a flow mod, sets up a rule that will handle those kind of packets, and then sends the packet back. Switch processes the rule, and that ARP packet then gets forwarded to host 2. So now host 2 has the MAC address of host 3, and it can form up the ICMP echo request packet and can send it, and so forth. And so, those are the activities that are going on in the response of the controller. At the same time, the controller and the switch have this kind of continuous asynchronous conversation that ensures that the connection is alive. So on the Wireshark trace, you probably saw things like echo and echo request. Those weren't related to the pings you were doing. They're simply part of the OpenFlow protocol, designed to ensure that the switch and the controller know more immediately if they lose connections to each other. So any questions about that exercise, what you saw, what was going on?
Okay, one comment, Steve.
Okay.
Hi, I'm Brian Pinkney with Internet Network Services, and so my question is, if the switch were to lose the controller, being that if it's in OpenFlow mode, it's not forwarding, it doesn't have any knowledge of, or it doesn't follow the standard knowledge of learning and forwarding. So if you lose access to the controller, what does the switch become?
Okay, so Ed, I got part of that. I think.
Yeah, so the question is if you have a pure OpenFlow switch, what happens when the session between the controller and the switch fails for whatever reason, say network disruption? What is the switch capable of doing at that point?
Okay, so there are 2 modes that the switch can be configured for. One is called fail secure, and the other is called fail open. And you configure these outside of the OpenFlow protocol. So for example, there has to be some way to configure the switch to tell it its IP address and what controller to point to. And there's also a way to tell it how to fail. And in fail secure mode, the switch will just continue to use the flow entries it has. And if some of them have timers, those timers will be will affect how the flow lives in the switch. The switch can also be configured to fail open. And in the 1.0 spec, fail open means the switch will behave like a learning switch. It'll behave like a learning switch just on its own. There are more sophisticated approaches to this in newer versions of OpenFlow, but those are the basics for 1.0. There are also facilities for identifying more than one OpenFlow controller for a switch. So a switch could have like a primary and a backup OpenFlow controller. And those OpenFlow connections are actually concurrently active. I think there's something in the protocol that allows the switch to say which one is primary. Any other, did that answer the question?
Yeah, I think so.
Any other questions? Okay, so in the window where you had started OBS controller, if you use the ampersand to push it in the background, you can, at that shell command, you can type FG return, and that will put it back in the foreground, and then you can type Control-C and kill it. You need to do this because if you don't do this, further in the exercises, you'll have a problem. And we'll say, oh, you still have your controller running. So make sure that you kill the controller. Now again, I'm going to sound like the redundant guy on the end of the phone. There's this command line utility called OFCTL, and it's really useful to do lots of different things. Primarily, you're likely to use it to do debugging. You know, is what I see in the switch consistent with what I think the controller is telling it via my Wireshark dump, via what I think the application is really supposed to be doing. But you can also use OFCTL to actually insert flows in the switch. So first of all, let's make sure that you don't have any flows in the switch, and you can do that by executing this sudo obs OFCTL del flows dp0, and that should delete any flows that are in the switch. So you should go ahead and do that. Once you've done that, you should go to the next slide, and I want to talk about what we're going to do for a bit here. You're going to be issuing 2 commands on the command line. Each one will use OBS OFCTL to add a flow into the switch's flow table. And just to dissect the command a little bit, super user do means run this as super user, so it has full privileges. OF-OFCTL is the command, this command line utility. There's a keyword add flow, which says that the next information tells it flow I want to add. DP0, that would normally be the IP address and port number of the listening port on the switch that's talking OpenFlow. But in our case, it's a named device, so that's DP0. And then the flow we're going to put in is going to have the following properties. Its match field, or header field, the proper name for the 1.0 table, is going to say if the input port equals 1. And if you look towards the end of that command, you see ion underscore port equal 1. So this is going to match on things that come in port 1. And the actions define what you're telling. If the packet matches that, if a packet comes in and matches came in on port 1, the action is going to be what to do with the packet, and this says output port 2. And if you look at the next command, you're saying if it comes in on port 2, output port 1. Now you're also doing a couple things. You're setting the idle timeout to 180 seconds. So after 3 minutes, if these entries don't match any packets, they'll disappear. And you're also giving them a priority value. In this case, they're the same. So go ahead, and you should have gone through the process of deleting any existing flows. Go ahead and run these two commands, and then also, run these two commands, and also after you've run them, in the Mininet window, by the Mininet prompt, type h2 space ping h3, which will cause h2 to ping h3, and just verify that those rules are working. Once you do this, did the pings work? The ping should have worked. You should do this command, sudo obs ofctl dump flows. Look at how the switch shows you the flows that you just put in manually, and then look at the counters. Like, keep the pings going and do the dump flow thing a couple times, and look at the counters and see how they increase, and are they doing what you expect. Ed, tell me when you get a bunch of nods.
We got nods.
Okay, we're going to move up the stack a bit, and the rule we put in was port-based. So, you know, any packet coming in on a port, on port 1, you say go out port 2, and port 2 go out port 1. Now we're going to also put in rules based on the IP source address. So here's, I guess the line wrapping makes this kind of weird. But here are the commands where we're putting in a slightly different rule. So before you just cut and paste these in, I want to talk about them just for a second. If you look at the first command near the end, you see two things. This again, you're defining what in 1.1 they call the header fields. And the first thing you're saying is, this is going to be matching on packet type, so data link layer type, or DL underscore type, hexadecimal OX800. That's IP version 4. So you're telling it, for IP version 4 packets where I match the Ethernet type field of 0800, then I want to say, so I'm saying if that's the case, and the network source address is this value, then output port 2, and on the next command, I'm also saying for data link type 800, if the network source address is .3, then output on 1. Notice that I'm also setting priority values here, and these priority values are a little higher than the port-based priority values. So go ahead and put those in, and do the pings again. No, do not delete the flows.
Where do we look at the counters?
So you look at the counters running a dump flow command. So this command here. How many of you the pings don't work?
Couple hands.
Couple hands. Okay, so I suspect for those of you who the pings don't work, a couple things happened. The ARP table in those hosts timed out, and you also were idle long enough that the port-based rules timed out. And so if you did the dump flows, the port-based rules wouldn't be there anymore. And if they're not there, and the ARP, the entries that forward based on port, not on IP address, if those disappear, then when host 2 sends an ARP for host 3, host 2 will send that ARP, send a broadcast packet to the switch, and the switch doesn't have a connection to a controller, so it can't send that to the controller, so the switch just drops that packet. And if you have both rule sets still there, if you want, you can type the other ones back in, and you are doing the pings, you'll see for the IP packets, you should see the counters for the IP rules increment, but the port rules not increment. And the reason is because the IP rules have a higher priority. When you have a packet come in on port 1, it's going to match both the port rule and it's going to match also the IP rule. But since the IP rule's priority is higher, the flow entry that's going to be used is the one with the highest priority, and so its counters will be incremented. So if you were debugging stuff, you'd want to look at the counters to figure out if you had traffic flowing through, what entry that traffic was hitting, and you need to be conscious that the entries can expire, and with something as simple as a ping, if you don't have entries that handle the lower bootstrap process for a ping, which is an ARP, then it could fail. Any questions? Ed, should I move on?
Yeah.
Ooh, looks like I have a slide out of order. We'll skip that. I have 2 slides out of order. Sorry about that. Okay. So you guys have seen a reactive application. That was when the controller made the switch act like a learning switch. And so packets come in. If there's no rule for them, they go up to the controller. Controller puts a rule in. Controller sends the packet to the switch. Now, a couple of things might occur to someone who's a network engineer. And one of them is, gee, it seems like a lot of traffic could go to the switch, or it could go to the controller. And that's true, and that can be a problem. There are some tricks that happen to increase that efficiency. So, for example, 2 things can happen. The switch and the controller can negotiate that only a portion of the packet is sent to the controller. So by default, the controller could get the whole packet. And you might want the controller to have the whole packet because maybe the controller needs to inspect all of the contents of the packet in order for it to determine what rules should be applied. But if the controller is just going to inspect the headers in the packet, which would be the case if it was doing an Ethernet switch, if it was emulating an Ethernet switch, the controller and the switch can negotiate just to send the header of the packet. And the controller and switch can also negotiate the switch having some buffers. And so the switch can put a packet it's going to send to a controller in a numbered buffer. It could take the header of that switch, the header of that packet, send it to the controller with an index, what buffer the switch is holding the entire packet in. And when the switch sends the packet back down to the, when the controller sends the packet back down to the switch, it can tell the switch, it doesn't have to really send the packet. You can say, that packet you put in buffer number 2, pretend I just send that back to you. So there is a way to optimize how much data goes between the switch and the controller when the switch has to do a packet in because there is no rule for that packet. The other thing is switches that you can buy today where OpenFlow wasn't a feature that was evaluated early in the design process of the switch. Those switches can have a limited ability to get data that's in their data plane into the control plane and on a TCP connection to the controller. So Ed is laughing.
That's an understatement.
Yeah, so there are OpenFlow switches that are very much constrained in how many packet ins they can actually do per second. And in fact, the number is very, very, very low. So if you were designing an environment that was going to use the reactive model to populate the table and the switch, you'd want to be careful and mindful of the rate at which the switch can actually do packet ins toward the controller. And you'd want to minimize that to the extent you could. It's also the case that these table sizes in the switches can vary, and they can vary in complex ways. So for example, even though in OpenFlow 1.0, the abstraction is a single table, in reality, there might be multiple tables in a switch, and how efficiently they get used can vary on a lot of things. So I'll give you an example. I was talking to an engineer an ASIC engineer who works for a merchant silicon company at the Open Networking Foundation Working Group meeting. And he was explaining something to me that was fascinating. He said, we make these chips, and these chips have a layer 3 table and a layer 2 table. And when we do the OpenFlow implementation on our chipset, if you don't use the priority field, we can use space from both tables. In other words, if you have a layer 2 match, we put it in the layer 2 table. If you have a layer 3 match, we put it in the layer 3 table. And we can make maximum use of both tables. But if you all of a sudden start actually populating the priority field, then we have to throw the layer 2 table away because we have no mechanism in our hardware to prioritize a match across tables. And so if you just start putting values in the priority field, all of a sudden they have to rejigger how they're using the capability on their chip to implement OpenFlow, and the table size dramatically shrinks, even if you're just doing layer 2 matches. Other switch vendors will, they might put part of the table matching stuff in CAM or TCAM, and then they may put stuff that doesn't fit or or the hardware isn't capable of doing the match. They might put those in DRAM, and it might be a software process that processes those packets. So you can have a high degree of variability in the speed at which the packets are processed depending on the implementation. And early in, most of the switches you see today that do OpenFlow, they weren't thinking a lot about OpenFlow when those parts were being designed. We're starting to see switches that are coming out where the parts, the components, OpenFlow was a consideration earlier in the design process, and so they should do a number of these things a little bit better. But today, you really have to ask a lot of questions of the switch vendor, and you also need to have some capability to do some testing if you're going to start to install these in a production environment. Their capabilities can vary a lot. Now, having said that, there's some really useful applications that don't really stress these features. So, for example, this point-to-point thing Internet 2 has, which is actually kind of cool. So you can provision this point-to-point circuit in under a second, and it uses OpenFlow, so they have Brocades and Junipers, and they could have Cisco's, and they could have HP's, and it doesn't matter. It's using the same API and protocol to configure them. That is a proactive application, so you don't have to worry about the performance of sending the packet from the switch to the controller. And it's also a pretty simple application that only requires a couple of rules per switch per provision point-to-point circuit. So they're doing really something very simple. They're matching on the VLAN ID and just essentially plumbing a pipe through using the VLAN ID as the selector on each switch. Now, what's nice about this, it's not like they're configuring one VLAN. They can choose to change the VLAN ID, so they're treating that as a label, and they can make that label significance local, so that they don't run out of VLAN IDs if they were using VLANs in a traditional sense. So, they have an application that takes advantage of just a really small subset of the OpenFlow protocol and API, doesn't really have a significant impact on, or switch performance doesn't have a significant impact on this, and they're able to deploy production nationwide service. So, I want to make sure that people understand it's just that these features, some are complex and some are less complex, and the vendor implementation, some are more optimized than others, but it all depends on what you're going to do with them. That's critically important. Okay, so any questions about that before I move on?
I actually have a question. With the discussion of current switches not really being implemented properly and newer ones being implemented better, is it more of a matter of like Broadcom Trident versus Trident 2 kind of stuff, or is it the actual switch vendors that are not implementing things properly? Did you catch that, Steve? So the question was.
Yeah. So he's saying, is it merchant silicon or is it the switch vendors?
Yes. Yeah.
Yeah. Okay. So this is a really good question, and it gets me to tell a story that I didn't get to tell earlier because I was being sped along. So there's something that's really different, and this there was like an aha moment for me when I went to the not the last one, but the one before that, the Open Networking Summit. So I'm meeting with, so our campus, we have probably 100,000 devices on the Bloomington campus, and we have thousands of phone closet switches, and we're looking at, we have an upgrade cycle for those, and we're trying to figure out how OpenFlow will inform what we purchase in the next upgrade cycle. So we're trying to figure out what things scale, these issues of table size and switch performance and all this. And we meet with some engineers who work for Big Switch. So Big Switch makes a controller that might be the kind of controller we would use in a campus environment. And so we meet with them and we say to them, basically, we're going to need to buy some equipment at some point. What models of switches? Tell us under NDA. We won't tell anyone you told us. What switches should we buy, or which one should we be evaluating? Which models and vendor numbers? And they said, oh yeah, we can help you with that. We're really interested in the Trident 2 chipset. So they didn't say, look at this HP or the IBM or the Cisco, whatever. They said, look at stuff built on this merchant silicon. Now, what was so weird about that is, if you we have a virtual machine environment here at the university, and you go talk to those people, and if they're getting ready to upgrade their infrastructure, they will go to the hypervisor vendor, which happens to be VMware, and they'll say, which chip architectures should we be looking at based on our applications and how we use VMware? And the VMware folks will tell them, okay, here's this particular Sandy whatever, chipset, or these particular extended features, whatever. And then they'll go off and they'll look at different vendors and how those things are packaged. And so they'll look for, pricing and warranty and service and all that. But they'll go and they'll look and say, okay, Dell and HP and IBM, we're looking for this chip architecture. What are the packaging options? So it is both the merchant silicon and the firmware on the box. But I think the important, what became clear to me at that point was you really need to start to understand the capabilities of the merchant silicon, because if you buy the wrong kind of the device based on the wrong merchant silicon, it can never be fixed. So that's like a fundamental foundation, so that all of a sudden network engineers will be able to inform the process better if they understand how the merchant silicon works. I know that's a long-winded answer. I think it's both. The other thing is, I think you're going to see more. At the last networking summit, Intel did some presentations, and what I got out of those presentations is Intel has embraced SDN. Intel has embraced ensuring that there's good integration between OBS and some of their switches. And so they have reference designs and firmware that support SDN that are coming out. So it used to be the case that you might have a white label switch manufacturer, and those guys can sell to a place like Amazon because Amazon's big enough to manage the risk. But if a white label shows up at like a Fortune 1000 corporation, let's say show up at like Eli Lilly here in Indiana, Lilly's going to go, I don't know you from Adam, and this is way too risky for me to buy these switches from you. On the other hand, if a year from now, a white label company says, oh, we have an Intel reference design and Intel firmware and the Intel chipset, would you like to buy these? They might go, oh, well, actually the equation's different. If we're getting an Intel reference design and the firmware's coming from Intel, yeah, we might have you put the Eli Lilly label on these switches, and we'll buy them from you. So anyway, I think getting to understand what the switches do at some detail, having some ability to test them or to get testing information, knowing what the kinds of features and the behavior of your network. In fact, we think we probably can provide some value to industry by saying, okay, we look at our campus and these are the kind of metrics that you need to target if you're going to sell a switch that would work in a phone closet and support a reactive mode with these features.
So Steve, let's say that, in a world where you've got so many people that have limited cycles to actually do this testing and actually get to the point of, getting access to the specs on the chipset, at what point is in the sort of the maturation of this technology, is it going to be that there's like an OpenFlow approved stamp on products, or some sort of an entity that could provide that kind of vouching so that somebody could just come to trust that entity and not have to do all this investigation themselves?
So Ed just set me up. Thank you, Ed. InCenter, the place that I work, is actually under contract from the ONF to develop the test cases for 1.0 so that a vendor can bring a product in and have it certified as compliant with OpenFlow 1.0. And that will be ready probably next month. So the first vendors that will have the official stamp that says, yes, the ONF has said we pass the tests that allow us to say we're OpenFlow compliant. That's going to be an important piece, but it's not going to be enough information because those conformance tests essentially won't have performance and capacity numbers associated with them. So it'll give you some level of assurance, but it's not enough. It's unclear. The next tests are going to be for OpenFlow 1.3, and that spec is so much more complicated. It's unclear. Well, it's clear to me that there will be many flavors of, there's already going to be a couple flavors of 1.0. There are going to be many flavors of 1.3 conformance, and they're probably going to be chopped up based on use cases. So I would not be surprised if there's a data center version of that spec where you say, yeah, I've got the ONF 1.3 data center conformance. So that's going to be useful, but you're still going to need to understand performance and capacity issues. So today you see bus capacity or fabric capacity and packets per second forwarding and that kind of stuff. You're going to see some other metrics that need to be included, like packet in and flow mod rates, and you're going to see table sizes. So I think that you're going to see vendors starting to offer more specifications to help inform purchasing decisions. That's one piece. And then another piece, and let me talk about it before we get into FlowVisor, because I don't want to lose track of it. There's something I didn't quite understand until I went to the last ONF meeting. So there are a set of vendors that have merchant silicon that's designed to do certain specific things, like IP routing. And there's actually a ton of really good merchant silicon that does IP routing. And so there is a working group within the ONF that essentially their mission is to figure out how to expose those functions to the OpenFlow API and protocol. And they're doing it through something called table type patterns, TTPs, an amazingly bad name. But let me try to describe briefly what they're doing and what you're going to start to see in the future. So let's imagine that you have this chipset that does high-speed IP forwarding. And there's no way this chipset can do OpenFlow. It was designed to do IP routing, IP forwarding, not going to do OpenFlow. But you want somebody to integrate it into an OpenFlow orchestrated environment. So here's what they're doing, is they're saying, okay, we're going to take all the knobs that you could turn for this chipset, and we're going to expose those as though they were OpenFlow tables. So I'll give you some specific examples in the way this would work. So you've got this box that's an OpenFlow device that's really going to just route. And it connects to the controller, and it tells the controller, you know what, I'm a 1.3 OpenFlow device, and I support table type pattern number 48. And so somewhere there's this definition of what 48 means. And 48 means this, what I'm going to describe. 48 means this thing is a router, and you can put IP matches in table 3, and you can put an IP match with a mask, and it will treat that as its fib. So you can put them in table 3 using the normal OpenFlow protocol as though you were installing normal flow mods of type IP with the optional mask. And this device is going to interpret those as though they were a list of IP prefixes that it's going to do longest prefix match on. And maybe that's table 4. And maybe table 5 is exposed as a ACL table. And you can put layer 2 or layer 3 entries in here with the mask, and those will actually be denies or permits or whatever that the routing engine will install as an ACL. So you look like you're populating a table the normal way, but what's really happening is you're just filling up parameters for this layer 3 chipset and expects them in this table. Maybe there's another table, which is the ARP table. Maybe you want to control that, and they can expose that. So they'd say, okay, well, there's this other table, table number 12, and if you write, gee, if it matches on this Ethernet frame, then rewrite the IP address to this value. That's the kind of table entry you think you're putting in, that the device will interpret that as, oh, that's the direct association table or the ARP table that I'm going to use to decide how to encapsulate packets as they go to the next hop. So the vendors are going to say, you know, yeah, I've got this, it's a router, but it supports OpenFlow, and the way it supports OpenFlow is through table type patterns. So that's one of the things that's happening through the ONF. There are, the group is the Forwarding and Abstractions Working Group, either called the FAG, I think. I could have that wrong.
Let's hope.
Stop laughing, Ed. So that's what some of the vendors are doing. You know, the whole area is really the wild, wild west right now. So anyway, any questions about that before I move on to FlowVisor?
Well, this is Jim Warner from Santa Cruz again. I've got a slightly different question. A couple of minutes ago, you mentioned that that selecting switches to go in telephone closets. So there's a whole bunch of other sort of doofy switch features that you want when you put something in a telephone closet. Will OpenFlow have anything to say about, for example, controlling power over Ethernet or all those other kinds of things that you need to do to run a real organization?
So good question. So there are a set of features that I can imagine being within the scope of OpenFlow for things like a phone closet switch. So let me tell you the kinds of features that I think would be, and then I can describe the ones that I don't think will be. So for example, it's common now in sophisticated edge switches to have features like features that would prevent a rogue DHCP server, and features that would actually listen to DHCP lease offers and accepts that will ensure that if somebody tries to spoof an IP address on a port, if the IP address source doesn't match what the switch has snooped as a lease that's supposed to be on that port, it won't allow it. There are switch features that support different forms of IP multicast. They support kind of constraining broadcast traffic. There are lots of things, lots of features in switches that are important. Spanning tree, that are important in the features that have to do with the behavior of the forwarding data plane. I think it's very likely that those features will migrate to the controller, and those will be software applications, and that if the switch has a good implementation of OpenFlow, that's the way you will instantiate those features. So you buy switches as OpenFlow. You have, as part of your OpenFlow controller, this thing that enforces the DHCP lease thing, or you write it, or you buy some module, that kind of thing. There are things outside the scope of OpenFlow, such as PoE management. Right now, there's not much in OpenFlow that provides, let's see, there's a bunch of monitoring stuff that's not in OpenFlow. So if you were proactively monitoring the state of the power supplies, other alarms, that kind of thing. That's not really an OpenFlow right now. And there are probably a host of other things that aren't there. So I think features that have to do with the forwarding behavior of the data plane, those can move. Features that have to do with management outside of the forwarding plane management, maybe less likely.
Thank you.
There's also something, we're not going to talk about it, but there's something called OFconfig. So OFconfig is a kind of an extension of netconf. And the idea is that a switch might boot up, and that OFconfig would define one or more OF switch instances in that device. And so you'd have sort of a more conscious approach to doing things, some of which were within an OpenFlow context and others which are outside of an OpenFlow context. And there are a number of things where you're going to do that. So I'll give you a couple of examples. Today, in OpenFlow 1.1 and forward, there's explicit support for things like bonded interfaces and redundant paths. And you would configure the details of like the algorithm for doing the load sharing across the bonded interface and the detection of paths going down and redundant paths being put in place. Those things would happen outside of the OpenFlow config. So just like when I showed the OpenFlow config for an HP, you've got 50 lines of config and 20 lines are defining the OpenFlow config. You would have things outside the context of OpenFlow which would in fact have a relationship to what the OpenFlow could do. Would define how these interfaces behave in this bonded, but the abstraction at the OpenFlow layer is just they're bonded. And so when you send something out, it gets load shared out there. How it gets load shared isn't within OpenFlow. OpenFlow just knows that that interface is some sort of bonded interface, and when I send a packet there, something will, do the balancing. Okay, let me do a time check here. What time? It's like 11:30 there, right?
Well, it's 12:30.
12:30.
Yeah. So
How much time?
I believe we're at the minutes at the end, I think, right?
Oh, really? Okay. Okay, we're not going to be able to complete the FlowVisor exercise. Let me just describe briefly what FlowVisor is. I don't think FlowVisor, at least in its current form, is going to be, you're not going to see it in commercial products, I don't think. It's really ultra cool though. So I'll give you the short story on FlowVisor. FlowVisor is a piece of software that sits between the controller and the OpenFlow switch. And it talks OpenFlow to the switches and it talks OpenFlow to the controllers. So you can think of it as an OpenFlow proxy. So the switches connect to it thinking it's the controller. And the controllers get connected, it connects to the controllers and they think it's the switches. And then you set up administrative rules in FlowVisor that says, okay, this controller can only see these aspects of the network and can only insert rules that will affect this kind of traffic. This is what gives you the ability to do things like, if I've got a bunch of SCADA systems on the network or card key systems on the network, and I know something about them, let's say I know their Ethernet addresses, I can define a administrative rule in FlowVisor that says, only give this upstream controller the ability to put rules in that could possibly affect traffic to these Ethernet addresses. And the other controllers, I won't give them that. So I've got one controller that might be running an application just for the door locks, and I might put that controller within the domain of our door lock security group. Imagine we had one. And they would be directly controlling the network. They would be putting flow rules down in the switches in any of the switches perhaps in the network, but the flow visor would make sure when they tried to insert a rule, it would look at the rule and it would say, okay, is this only going to affect traffic that you've been given access to? And if the answer is no, the rule is too broad, it might affect other traffic, the flow visor then will try to add rules to come up with something that's more restrictive that will ensure that it only affects that traffic. Or the flow visor will just say error, can't add the rule. And this is a way to virtualize access to the network resources. These virtual pieces are called slices. The slices are given something called flow space. And flow space is network flows that match certain header values, like have these Ethernet addresses or these IP addresses or these VLAN IDs or these TCP port numbers. For example, you could put a controller in that could only control how traffic to and from TCP port 80 flowed in your network, would be another example. So I kind of felt we weren't going to get to this exercise because normally there's a couple more hours to the full day workshop, and this is one of the more intense exercises. So I hope this was useful. I apologize for not being there, and thanks for muddling through this with this disembodied voice. If you have any more questions, happy to answer them. And if you think of questions later, you can just send me email, or you can bug Ed, who knows all about this stuff.
We're all nodding contentedly, so I don't know if there's any further questions.
Thanks. Ed, thanks a lot. And would you tell Tony thanks too? He did the MC thing the first half.
Absolutely. Thanks, Steve.
All right. Talk to you guys later.
Do that. since it's now 9 o'clock local time, I'll get started. So this is the OpenFlow, hands-on OpenFlow tutorial, and I am not Stephen Wallace, who I'm Tony Tauber, who's on the program committee and worked with Stephen on getting it set up. Stephen, unfortunately, through some airline mishaps, was unable to make it, but is here through the owner of the internet. So this is actually his presentation laptop being shared on the big screen, and he's hearing us through audio, and he'll in a minute too. So the story is that there are these two Google Docs. Slides are down at the bottom, which is what he'll present, but you can always refer to them and skip ahead or look back or whatever. And then sign-in roster also is a Google Docs spreadsheet, which is important to use the hands-on aspect of the exercise. And what it is it'll give you an assignment for a virtual machine that's hosted on Amazon Web Services. You can participate in the hands-on part of the session. It's not easy if you're feeling shy to necessarily use your real name and all, but it will. What you have to remember is which line on the roster you filled in, so that you can, because that'll be which it'll translate to which virtual machine you are assigned to. So that's very important to do for the hands-on piece. And I think the hands-on piece comes a little later, right, Stephen?
Yeah, it'll come quite a bit later, although what I'll do is to try and identify and sort out any problems ahead of time. Those who want to do the hands-on piece fairly early will be asked to just make sure they can get access to it.
On my part of the, can folks hear me all okay out there? So I see that people are indeed filling in the speak as we speak. I've got it on the lower part of my screen. So we had a couple of people come in to the end there, and probably, knowing the way things go, will be a couple more stragglers. But just to let you know, Stephen Wallace presenting remotely, and I'm helping facilitate. But as far as the questions, I think he can hear somewhat what's going on in the room, although it's hard to interrupt, obviously, because he won't be able to hear you that loudly. But so I'll be trying to moderate if there are questions or whatnot. Again, for those few people distracted, Stephen Wallace is going to present this hands-on OpenFlow tutorial, and but it should be pretty much just as effective because we've got all these technological tools at our disposal. Again, these are the slides on Google Docs, and then the registration roster, which is in the exercise. I need to register, just listen obviously, and it's not to register with your name if you are feeling shy about it, but it's important to still hands on correctly. Okay, so with that, I'll hand over to you, Paula.
Okay, I apologize for not being there. Just for the curious, I had a flight from Indianapolis to delayed due to weather in Atlanta, and I missed my thing. And apparently all other flights from Atlanta to New Orleans, or any other reasonable other line even for getting to New Orleans last night, did not exist. So that's one other. Would you let Tony know if you guys can hear me okay?
Thumbs up.
Cool. Okay. All right. So as Tony said, hands-on later. But if you're interested in participating in hands-on, go ahead, go to the slide. You put his name. Doing is you're reserving a number, and what you want to kind of write down in that spreadsheet where you put your name or pseudonym, because pretty soon we're going to just to make sure that you can access the hands-on resources that are hosted by Amazon Web Services. So they'll have a domain will be that row number that you took up in the spreadsheet. This is just a deep way for us to do a unique number to make sure that you're logging into a unique VM. Any questions about that?
Anybody? Okay.
Cool. And I've never done this in this mode, so bear with me. So what you're here for is something we call OpenFlow, and it's really going to be and it's presented by InCenter. InCenter is the Indian Center for Network Translational Research and Education. We kind of research on something called Global NOC. The Global NOC is the Network Operations Center at Indiana University that operates a number of regional, national, and international networks. The biggest, best known of those networks is probably the Internet 2 network. It's actually a pretty substantial resource. So there are roughly 100 full-time people who work directly or indirectly for the Global NOC. and all of their focus is external to Indiana University. So they, in fact, don't run IU's networks. They do run the regional network in Indiana, but their focus is on external networks, and they, for the most part, their funding, most of their funding comes from those networks supporting them to provide the operational support, and they do everything. So they have, for example, they have a couple folks who just travel to physically install stuff all over the world, and they develop their own software. They have a software engineering group with about 20 people. They have, I think, roughly about 20 high-level engineers. They probably have 20 people who focus on manning the 7x24 by 365 help desk. So it's a fairly big operation, but their focus is on research and education networks, and those probably have qualities which are in some ways different than the commercial networks. If you want to follow up with me, if you have questions that you didn't feel were answered during the class, or you had thought of them during class, you're welcome to. My name's Steve Wallace, and my email is simply ssw@iu.edu. Okay, some of the tools that we'll be using today. The hands-on section will use VMs hosted by Amazon Web Services. If you haven't used AWS, it's pretty easy and it's kind of cool. So first of all, the VMs that we'll be using are based on what are called public AMIs, public Amazon Machine Images. So you can create an account on Amazon Web Services, and when you create an account on Amazon Web Services, you get a fair amount of free time on what are called micro instances. These are relatively small VMs, small in the sense of the memory and disk space and CPU resource. It's possible for you to spin up the same VM that we'll be using in the hands-on exercises on your own. So you could create your own Amazon account. Pretty simple. You could spin one of these VMs up and play with it. The VMs aren't that special. We've installed some software on them to facilitate the class. One of the pieces of software that we'll use is something called Mininet. Mininet is a virtual network environment, and its underlying switch is, in fact, Open vSwitch, and Open vSwitch supports OpenFlow. Mininet is a useful tool both to learn on and to develop against. So, for example, the IU develops software that controls some OpenFlow switches in the Internet 2 network, and so they have this application. The application is called OESS, and it presents a web portal to authorized users, and those authorized users can define a point-to-point connection across the Internet 2 network, and that web-based portal uses OpenFlow in the back end to actually put the rules in the switches that implement that point-to-point network. Well, when the folks who are developing that software need to test its features and its scalability, one of the things they test it against is Mininet. So Mininet's actually pretty useful for education testing, those kind of things. We doing okay so far? Excellent. Okay, Mininet uses something called Open vSwitch, and Open vSwitch is, again, it's an open source vSwitch. Typically, you see Open vSwitch in a VM environment. So if you had a server that was hosting a number of VMs, Open vSwitch might be the switch between the VMs and the physical network outside the physical server, and that provides a real flexible ability to provide services that do things like separate tenants, provide virtual networks. Open vSwitch is it's an open source project, but it's controlled somewhat by what was formerly Nicira and is now VMware. So it is an open source project, and you can take the source code from OVS and fork it and start your own project. And I think last time I looked, there was about a dozen forks of OVS on GitHub, people doing various things with it. But there is a core set of contributors. Most of those contributors, last time I looked, were with Nicira, and they essentially control the contributors and what finds its way into sort of the official Open vSwitch distribution. A lot of folks who are developing software-defined networking stuff for data centers, multi-tenant data centers, rely on OVS, and so there has been some tension in the community, not a lot, but some folks that rely on OVS and would prefer that the OVS project be a little more democratic or a little more transparent. So another application that we'll be using on these VMs is something called Wireshark, and you're probably familiar with Wireshark as a network sniffer. We're going to be using Wireshark's ability to decode the OpenFlow protocol, and as of today, Wireshark, the standard distribution of Wireshark, does not include the OpenFlow dissector. So we have built a version of Wireshark on this VM that does include the dissector. The good news is, at the last Open Networking Summit meeting in California, we were able to spark a good discussion with some folks that were more closely related with the Wireshark project, and that discussion has been ongoing, and it looks like we're getting closer to the OpenFlow dissector code finding its way into the standard Wireshark distribution, which would be fabulous for the folks who are doing OpenFlow development.
Hey, Steve.
Yep.
It's Tony. I'm just going to pause for just a moment since a few more people have drifted in, to just give them the background here. So Steve Wallace, who's presenting this tutorial through some airline problems, was unable to physically be here, but I'm Tony Tauber from the NANOG program committee and helping to get things set up and so that Steve can present this remotely via Skype. And these are the URLs at the bottom of the workshop slides, so you can follow along. I mean, it's what he'll be showing on the screen, but you can also refer to them, look ahead, look back. You can look at them later. And then the roster URL, these are both Google Docs documents, and the roster URL you can sign in for a virtual machine, which we'll be using during the OpenFlow, during the hands-on part of the session. So that's what those URLs are. And I'm going to give it back to Steve, who will be the disembodied voice you hear.
Tony's channeling me, which is great. So the two URLs, one is for the roster at the top, and the other is for the...
It's got a little mishap with the display here. Let me just see if I can reboot that display. Huh. All right, keep talking. I'm just working on the display here to see if I can get it back in order.
The roster slides are tinyurl.com/nanog58-roster. And again, you don't have to put in your real name, but if you want to participate in the hands-on, you need to put an entry in that spreadsheet and remember the row number that you used to put that name in. And then you can also follow along with the slides. For example, if the projection of the slides gets messed up, like it might be now, the slides are available via tinyurl.com/nanog58-slides. So hopefully those will be useful. When you get to the hands-on exercises, you're probably going to want to have the slide deck in front of you. Otherwise, you're going to be managing both having typos and learning new stuff. So.
Not yet quite there.
Okay.
Just trying to get.
So I'll talk about a couple things that aren't in the slides, why Tony works on getting this stuff back up. So I'm going to talk about in the presentation about where OpenFlow came from and the nature of the standards body that maintains OpenFlow. But the other thing I should mention that's not in the slides is something called the Open Daylight Project. So there is an open source project organized under the Linux Foundation called the Open Daylight Project. And my understanding of the Open Daylight Project is it exists to produce an open source OpenFlow controller. And I think you'll have a much better sense of what an OpenFlow controller is later in the presentation. And in fact, I shouldn't say OpenFlow controller, I should say software-defined networking controller, probably with some emphasis on OpenFlow as one of its southbound interfaces. So the idea is it's a pretty high-profile project. It has some significant contributors, including IBM, Citrix, Cisco, Big Switch, which is one of the a startup in this software-defined networking space, as well as many others. There's a web page for Open Daylight. Dave Meyer is involved in that project, and he's attending. My understanding, he is attending NANOG, unlike me, live in person. And
yeah, Dave's actually in the back of the room.
Excellent.
But, so I'm trying to sort out the display problems here, which caused the display to kind of go all wiggy and jumbled. And are you still sharing?
I think so. Let me double check. I have to kind of go out of. No. Let me reshare with you.
Part of my screen is still
actually, it says I'm going to stop sharing and then I'll start sharing.
Okay. Let's see how that works.
So I just restarted sharing.
Yeah, right. So now we see your screen.
Okay. Okay, cool. Let me put it back in presentation mode so it's easier to watch.
Okay. Cool. All right.
Okay, so just to finish up the thought, the Open Daylight Project is, Dave is provided some really fantastic leadership, and part of his leadership is to make sure that it's operating very open and transparently. And so my understanding is the calls where they discuss what they're doing and why and how and all those things are open. And at some point during the workshop, I think Dave might take a little bit to talk about his perspective on OpenFlow and Open Daylight. So maybe at the next technical problem if Dave happens to be in the room.
Yeah. So Dave is here. He's stepped up to the mic, and the technical problem is unfortunately still dogging us a little. So I might let me see if I can change.
Can I just say something while you're doing that?
Yeah.
Okay. Wait a second. I got to read this thing here. It's guidelines.
Okay.
State name, Dave. Affiliation, well, Brocade, U of O. So just to follow up on what Steve had said there, what we try to do with this daylight thing is make it as transparent as humanly possible or machine possible or whatever. So the way that translates is all of the technical steering committee calls are open, and the mailing list is open. You can even talk on the TSC call. It's just a WebEx, and there's a wiki on wiki.opendaylight.org. And if you scroll down to the TSC link, you'll see the agenda and all the WebEx information. And if you look at lists.opendaylight.org, all the lists are there, including the TSC list, which is the one we use to communicate on. And you're more than welcome or encouraged to join and see what's going on. Because at the end of the day, it's an open source project, and unless it's completely transparent, it'll fail. So, come along, listen, watch, whatever you like. Write some code even.
Okay. So I'm gonna, I just disconnected the display, and I'll try and connect it again. Let's see how that works. Okay. I'll try it with mirroring. Maybe that'll have a better outcome. Okay, you might need to reshare, unshare and reshare again, Steve.
Okay. So I'm stopping sharing. Tell me when you want me to start again.
Go.
Okay, share screen. Yes.
Okay, yeah, we see it. All right.
Cool.
All right, looks good. Okay, carry on.
Okay. Thanks, Dave. Dave, do you want to say any more?
Nah, he's done.
Okay. All right. So one of the points I would like to make early on is we're going to talk in some detail about OpenFlow protocol itself, and it's sort of like back in the day when, at least when I learned HTML, I actually learned what the tags look like. And when I first wrote HTML, it was actually manually putting the tags in, and there wasn't a WYSIWYG editor. And if you took somebody who didn't know anything about what the web might be in the future, and you were teaching them about the World Wide Web by showing them these HTML tags, they might have a kind of a limited view of what was possible with this. And so I just want you to keep that in mind during this workshop, that when we focus on OpenFlow, it's kind of a low-level thing. It has some potential to change approaches to networking, and I'll talk about that in specific use cases. Some people are really skeptical about it, and in fact, Dave is probably one of them, which is healthy. But anyway, so you're gonna learn. I'm gonna be talking about the equivalent of tags in the real world. People will be using the equivalent of a WYSIWYG editor when they're using or a content manager, something much higher level, but that was useful to start off with kind of a low-level understanding of what this stuff is. Okay, so just to make sure that you guys really do have access, although there's some limit to what I can do if you don't, these are the instructions. Now, before you do this, let me say a couple of things. It's been our experience during workshops that many folks no longer use X servers on their laptops. And so, so we've come up with another way of accessing the VM. So if you go to the lower part of the screen and you just type http://vmx, X would be, you need to replace X with the row number in that spreadsheet, and then use the rest of this URL. What you should see is a Linux desktop rendered in your browser, and so we're using something called Guacamole, which is really pretty freaking cool. Guacamole is essentially a transcoder between things like VNC and dynamic HTML. So what you should see with no other browser plugins is a login screen, and the username is OpenFlow, one word lowercase, password is OpenFlow, one word lowercase, and if you enter those credentials, you should see probably a Wireshark window and a couple of shell windows on the VM. So grateful if those of you who want to do the hands-on try this and then let Tony know it works or doesn't work.
Yeah, hold on, I'm just trying to straighten out something with the display again here. So, it worked? Good. All right, people are encouraging.
Most excellent.
Let me just, I have this one thing that's supposed to keep this screen alive, and I don't know if that's what's causing the upset here. Shoot. All right, well, carry on. We're dealing
Okay.
with some not great video, but it's okay.
Just as a reminder, that you guys can look at these slides on your own systems. And I apologize if this is kind of rehashing old stuff, especially if you folks attended the shorter version of this we did the last line of NANOG. But some of the feedback we've gotten is it would be good right off the bat if you told us why we even care about this. And so we kind of break down the why we even care into three areas, what I would call the enterprise, the data center, and the wide area network. And so just quickly, what can this do for the enterprise? OpenFlow provides a standard way to do configuration of your networking equipment. Now, it's of course not the only way to do this in a standard way, but it does provide a single API and protocol that you can use to configure the network equipment that you put in your enterprise. In theory, there will be applications that run on top of the OpenFlow controller. So for example, an OpenFlow controller might be the Open Daylight controller that comes out of the Open Daylight project. And there might be applications people write that do things like provide network services geared towards payment card industry security requirements, or provide a nice uniform way to do network access control, where if you have a new person entering your network and you want to make sure that they register their device and are authorized and all that kind of stuff. Potentially, it would allow you to virtualize part of your network so that you could have what might be called slices of the network that are used for things like the closed circuit TV or the SCADA systems or the door locks. And that delegation of control of the network could allow another part of your organization to actually run that piece of the network. And it's not a physically distinct piece. So for example, you could have this network that was comprised of just a bunch of OpenFlow switches, and you could delegate control of the traffic for your door locks. Let's say that your door locks, you need the MAC address of all the network connected door locks. You could actually define a slice of the network that only could control traffic to and from those MAC addresses, and you could delegate that control to some other part of the organization, even though the door locks are plugged into the same switches that the users and the wireless access points are plugged into. OpenFlow also, because it's a pretty flexible API, could allow you to address new unmet needs. So for example, we have a test implementation of something that allows folks at IU, so we have these things at universities, we have these things called faculty. And faculty are, they expect things to behave in a certain way, and they're the most important people on campus. It's not really students, it's generally faculty. The faculty sit at home and they'll have an iPad, and they can easily take what's on their iPad and put it on their television using an Apple TV. And so they come to our advanced classrooms on campus with their iPad and want to know why they can't just put what's on the iPad up on the video in the classroom. It's so simple at home, why can't they do that at work? Well, that particular application relies on something called multicast DNS for the Apple TV and the iPad to sort of locate each other, and for that service to get bootstrapped. Well, in an enterprise network, at least in our enterprise network, the wired network that connects to the classroom video infrastructure and the wireless network in that classroom are separate subnets. And multicast DNS doesn't really jump across the subnets, and so it just doesn't work. And so You can use something like the programmability of an OpenFlow network to bridge, just for multicast DNS, those networks and offer a solution that's pretty easy to implement to support things like share your iPad on one of our classroom screens. And sort of the mighty message here is in the software-defined networking space, software-defined networking promises to more closely connect your applications to the network so that the applications would be able to more easily in a standard way cause the network behave in a certain way. What can OpenFlow bring to the data center? Well, again, standard API for provisioning stuff, and this becomes more critical in a multi-tenant data center. So if you look at something like Amazon Web Services, if you want to configure a VM on Amazon Web Services, you get on a web portal, and it literally can take a minute or two to go from no configuration to actually spinning up a VM in AWS. And it's not really much harder in AWS to have a load balancer and have multiple VMs in their own virtual private cloud or cluster in AWS. And so you can do all these things via the web portal, and this software that Amazon develops, their orchestration software, makes all this happen behind the scenes kind of in an invisible, transparent way. It's fully automated. When you click the spin up button on the web screen, and the network is dynamically changed as well as the VMs and everything else you need to essentially spin up whatever instance you've requested. So it's critical for the multi-tenant data centers to have the ability to program their provisioning of their network resources. OpenFlow provides a standard, or potential to provide a standard API that extends from the vSwitches that are in the servers all the way out to the physical switches in the room. And it can allow you to have new network behaviors. So you can use OpenFlow to program the switches in the data center to behave in a way that's completely different than the way a normal Ethernet switch behaves. And the reason you might want to do that is there are ways in which you might address a scaling problem differently if you could have a different behavior in the switches, and I'll talk about those in a bit.
Hey, Steve.
Yep.
It's Tony. Just still dogged by this these video problems. So, how about for people in the room, if you could follow along for now until I try and resolve this. So the slides are available at tinyurl.com/nanog58-slides. And Steve, if you could just give them an indication of what slide you're on so that they can follow along while I try and get the video back up on the screen. So do people get that? So it's tinyurl.com/nanog58-slides, and that's the Google Doc. So what's
dash slides, right? Not slash.
Yeah, dash. Sorry. And we'll try and get the video the screen back up in a second. My display is completely freaked. So what slide number are you on now?
So I'm on slide number 9.
Okay. All right.
And slide number 9 is labeled "What can OpenFlow bring to the data center?" And so the last point, OpenFlow is a potential target for original design manufacturers. These are sort of the off-label or white label switch manufacturers. OpenFlow gives them a sort of a target interface to implement that provides a level of standardization so that there's less, I guess they call less friction between a white label switch company building something that you can easily then incorporate into your data center. Going to slide 10. What can OpenFlow bring to the wide area network? Again, standard API for provisioning of network services. Initially, the stuff I'm familiar with in the Internet 2 network is OpenFlow is the standard API for provisioning bandwidth on demand services. So on Internet 2, you know, you get on this portal and you can define a point-to-point path and maybe a backup path, and you can say I want it now, or you can say I want it in the future, and it will provision that path using OpenFlow. And today there are both Brocade and Juniper switches in the mix of devices that are provisioned via OpenFlow. And in theory, they'd be able to install different kinds of switches, more than 2 kinds, in this network, and the software would remain the same. It would use OpenFlow as the mechanism to make the changes in the switches. I've talked to some of the vendors in the WAN space about what they see as useful from OpenFlow, and one of the early things I heard was a standard API for addressing lawful intercept requirements. So rather than relying on a feature set from a vendor, and they may be incompatible feature sets across vendors, they saw OpenFlow as potentially a way for them to implement lawful intercept in a uniform way across different switches and different vendors. The other thing that I hear from vendors, and I was hearing it from Verizon, did some presentations kind of before I became very familiar with the network functions virtualization push, was something I would call service insertion. So if you listen to some of the Verizon folks talk about what they're interested in, they have this vision that, and the way they describe it is, let's say, you know, they're offering a service which is streaming video over the network, and their network consists of, you know, a wireline network, their fiber network, as well as wireless network, and maybe you're watching the streaming video on your wireless device, and they can take information from the wireless infrastructure and know something about the network. So for example, maybe it starts raining heavily near the cell tower that you're receiving a signal from, or maybe many more users are now connecting to that cell tower. And for whatever reason, the native encoding of that video is not optimal for the kind of network service the cell tower's able to give you in these conditions as the conditions change. And so they talk about using OpenFlow as a way to reroute that video flow in some cloud of services that they maintain, and so they can take the knowledge that they need to transcode this to give you the optimal experience, and then they can take that individual video flow and route it to a transcoder. So it essentially inserts the transcoder in the IP flow, transcode that to a better bit rate to deliver you a better experience. And they see OpenFlow as one of the tools that would allow them to essentially steer that flow around at that fine granularity. The folks interested in network function virtualization, I think, see the same potential, that OpenFlow may be a tool used to insert these services which may be running in some sort of lightweight VM in the network equipment. So I think it has potential to provide that. And the other thing that we see a lot of this in the academic space. It's not clear to me we're going to see much of this in the commercial space, is using OpenFlow to delegate control of a part of the network. I mentioned this earlier. Maybe you had a slice of the network in your enterprise that was used for the closed circuit TVs or the door locks. Well, in the wide area network, you might have a slice of the network that you provide to some user. So for example, pretty soon Internet 2 will offer slices of the network for researchers. So a researcher would be able to write their own OpenFlow application, have their own OpenFlow controller, and be able to request a, quote, slice of the Internet 2 network upon which to try out their service.
So Steve, I'm just pausing to let people know we're working on getting another laptop to just throw up on the screen. So the complication here is that Steve's Skyping in through my laptop, and that's the audio. Otherwise, I would reboot to try and resolve the video problem, but then we lose the audio altogether. So we're going to try and throw up the slides on the screen so that people will be able to see them in the room instead of having to follow along on their laptops, and we'll keep the audio flowing through my laptop, at least till the break, and then we'll try and reboot. So carry on. What slide are you on now?
I just turned to slide 11.
Okay. And again, that's tinyurl.com/nanog58-slides.
And does anybody have any questions up to this point? No. Okay. So a bit about where OpenFlow came from. There was something called the Clean Slate program at Stanford. And as part of that program, there was some work on a new idea for securing networks. And I find this kind of fascinating. So there was some work on developing networks that would be ultra secure. So you can imagine, when you connect to the wireless network at NANOG, you basically connect to the entire world. You're getting an internet connection and you can reach anything. But you can imagine situations where what you'd like to happen is that you connect to a network and you really don't connect to anything. And so there's some agent on your laptop that has your credentials and has to ask the network for each connection that you want to make. So if you want to talk to a local server, you actually have to make that request of the network, and the network would check to make sure you were authorized. And then the network would actually set up a path just for you to that server for, say, some specified amount of time. So you'd want the network to, by default, not provide any connectivity. And if you did that, since the networking devices we have today, things like Ethernet switches and so forth, default try to make everything connected, you need a different way of controlling those devices if you wanted to test this out in real life that allowed you to have control and allowed you to make them behave differently. And that's where OpenFlow came from. It came from the need to be able to control these Ethernet switches to provide a fundamentally different kind of network service so that the forwarding could be controlled at the flow level. So that's where it came from. In 2009, Stanford published the OpenFlow 1.0.0 specification. Around that same time, Nicira got some initial funding. Shortly thereafter, Big Switch got some seed funding. Nicira and Big Switch were software companies specializing in developing OpenFlow controllers or SDN controllers. In 2011, the Open Networking Foundation is created, and the standard is sort of transferred from Stanford to the ONF. And there's also something called the Open Networking Summit, which is separate from the Open Networking Foundation. This is all confusing. But at the 2012 Open Networking Summit, Google makes a really pretty big announcement that Google has two wide area networks. So they have a wide area network that interconnects their data centers, and they have roughly a dozen or a little over a dozen data centers. And then they have the wide area network that connects us, users of Google, to their servers, when you type google.com. Google makes the announcement during the 2012 Networking Summit that they migrated their inner data center network to an OpenFlow network. And that all of the data that traverses that network is directed via switches that are supporting OpenFlow. So pretty big announcement. They weren't announcing they were going to do that. They had actually announced that they had done it. Their migration had started in 2009. They built their own switches to support OpenFlow, but they said during the Open Networking Summit that they didn't really want to build their own switches, that they had to, but they sort of signaled to the crowd, and the crowd included lots of people from vendors that in the future maybe they would buy switches. They really wanted to see OpenFlow take off. Okay, going to the next slide, slide 12. So as I said, the Open Networking Foundation sort of received the standard from Stanford. And the Open Networking Foundation is a membership-based, not-for-profit. There are a lot more members of the ONF than are listed on this. I made this slide probably about a year ago. The ONF board is made up of companies like Deutsche Telekom, Facebook, Google, Microsoft, NTT, Verizon, Yahoo. I think Goldman Sachs is on the board now. And these board members don't really make equipment to sell. They develop services that rely on equipment. And so the board, the core governance of the ONF is folks that want to see things like OpenFlow succeed, not because they want to sell products like switches that support OpenFlow, but rather that they want to develop infrastructure and services, and they want OpenFlow to be a viable option in their toolkit for developing those services. Right now, I think there are about 95 members of the ONF, and basically everybody who makes network equipment is a member of the ONF. Moving on to slide 13, a little bit more about membership in the ONF. It's been a little while, but I think this is still true. Being a member of the ONF comes with a $30,000 a year membership fee. The members agree to share any intellectual property required to implement something in the OpenFlow spec on reasonable terms. They have working groups that evolve the standard, and the membership in the working group is restricted to ONF members, although there is an exception. The ONF has something called research associates. And last time I was at an ONF meeting, I think there were roughly a dozen research associates. Typically, the research associates are from higher education and research, so that it doesn't really make sense for something like an Indiana university to be a member of the ONF. I mean, the ONF membership isn't really structured to support those kinds of memberships. But for Incenter to work with the ONF and develop things like OpenFlow conformance testing, we need to participate in the interoperability and testing working group. So for example, the manager lab, the Incenter SDN lab at IU, Ron Milford, is the vice chair of the ONF interoperability and testing working group. And to accommodate that, he is a research affiliate, I think is the term, within the ONF. But unlike the ITF, where generally you can kind of self-select to be part of an effort in the ITF, to be part of an effort in the ONF, you really have to be associated with an ONF member. couple things. Why is OpenFlow happening? Why is there a buzz?
Are we on slide 14?
Yeah, sorry, slide 14. I guess I should beep. Why is there buzz about OpenFlow? Why does it exist? I think in part there's a critical need for the large multi-tenant data centers. So the Amazons, the rack spaces, the folks developing multi-tenant data centers, and in fact, there are large companies. I spoke to some folks from Goldman Sachs, and they essentially operate a multi-tenant data center because of regulatory requirements. They have to provide a certain level of isolation between different groups within Goldman Sachs, but they still want to leverage, to the extent possible, a common IT infrastructure. So if you're going to have sort of these multi-tenant cloud environments where you need to have the full orchestration automation, you need to be able for people to go to the web and say, I want this, this, and the other thing, press a button, or you need an application to basically make a request of resources and for that application to signal via some API that it needs additional resources or needs to give back resources, needs to scale down. You need that kind of automation. Then a standard way of configuring the behavior of the Ethernet switches, both the vSwitches inside the servers and the physical switches in the data center. That's really a compelling case. In the large data centers, the large data center operators like Amazon, they're large enough that they can develop their own orchestration software to do all this. And so I think SDN and OpenFlow probably have a pretty strong footing in places like that to meet those needs. And those places are big enough that if that's true, that's probably enough of an ecosystem for OpenFlow to sustain and grow. There are also, I alluded to this earlier, there are things you can do with OpenFlow that you can change the behavior of switches. You can make switches do things that switches normally won't do. And some folks from Juniper find a term, they call it floor plan entropy. And multi-tenant data centers have this thing, it's sort of like disk fragmentation in that if you're offering elastic services, you might have a tenant that initially allocates lots of VMs and uses lots of resources. And maybe when they're initially allocated, they're kind of close together. And so if they have communications requirements, they have a lot of data moving around among the VMs. They might physically be in the same place. Maybe they're in the same rack or near each other, maybe a rack apart. And so the capacity is easy to arrange among those VMs. But because the environment is elastic, then that customer can reduce their VM requirements. Another customer can come in and need resources, and they might take up the unallocated resources of the first customer. So now the first customer needs to expand some, and those VMs that were close by are in use. So that new expansion needs to take place somewhere else in the data center. And so what you have is, as these demands come and go for multiple tenants, you essentially get the structure of the tenants has this increasing entropy. In other words, they tend to be scattered around your physical resources. Now, you can do things to try and migrate them back or try and ensure that they tend to stay together, but that's an imperfect, those techniques tend to be imperfect. And so if you're building a network for multi-tenant data center, what you really want to do is you really want to try to ensure that you have maximal bisection bandwidth from anywhere to anywhere in the data center. Now, if you have a really big data center and you have maybe 1 million VMs, and you want to do some sort of flat layer 2 thing, that doesn't scale very well because if you have some sort of flat layer 2 thing going on, then you have a million VM data center, you start to have to worry about the table sizes and the switches. And the more CAM or TCAM you put in a switch, the more power the switch is going to consume, the more switch is going to cost. And at some point, that becomes kind of a prohibitive way to design a data center. Now, there are other ways to attack this problem, but one sort of OpenFlow-centric way is to say, well, we'll use the Ethernet address differently in this scenario. Maybe we will have a pseudo MAC address for each VM, and we'll actually encode in that MAC address some routing hierarchy. So maybe we use the first 2 bits in every MAC address, every pseudo MAC address, to indicate what corner of the building the VM is in. Now, if you're doing some flat layer 2 thing, the switches in the center, which under normal Ethernet behavior might have to hold the entire table size, maybe they only need to look at the first 2 bits in the Ethernet addresses. Maybe their table size is essentially 4 entries, 1 entry for each corner of the building. And when a packet comes in for a particular destination, maybe that switch just looks at the first 2 bits and says, okay, it needs to go to the northwest corner or the southwest corner or whatever. And so you can build hierarchy, routing hierarchy, into the existing Ethernet address, and OpenFlow would give you the ability to have the switches behave completely differently, have the switches just look at those bits to make the forwarding decision. So that's just an example of how you might use OpenFlow to create a new behavior in a device that gives you another option in terms of solving a problem. Okay, so I'm getting some notes saying I'm going a little too long on these and I need to move more quickly. All right, so let's move along. So I'm going to buzz through a couple slides really quickly. 16, reducing the oxygen requirement. The only interesting thing here is the term merchant silicon. If you haven't heard that before, you might want to click on the link or look that up, but that's an interesting change. A long time ago, companies would focus on building their own silicon, and now a lot of the packet forwarding silicon is made by companies that make packet forwarding silicon and will sell that to any vendor. All right, so starting at slide 17, what is OpenFlow? It's a protocol for controlling the forwarding behavior of Ethernet switches in a software-defined network. You can have a software-defined network which does not have anything to do with OpenFlow. But one example of how to do software-defined networking is using OpenFlow. And most of the stuff that we're going to do today, including the exercises, is based on OpenFlow 1.0. The switches you see today, if you can actually purchase the switch and it supports OpenFlow, usually support 1.0. There was a huge change at 1.1. And the current approved spec is 1.3, and we'll talk about the differences in those later. Going to slide 18. This is the kind of the Ethernet switch. Today you've got an Ethernet switch that has control plane and a data plane. The data plane is the part of the switch that has the high-speed forwarding hardware. Frequently, these switches use TCAM or CAM, content addressable memory, or a ternary content addressable memory, basically to build a table that defines how the switch behaves when a packet comes in. So a packet comes in the switch, it's compared, usually its destination address is compared with one of these tables, and an entry in the table tells the switch which ports to forward that packet out. So that's today's model. And if there are advanced features in the switch, they're usually implemented in the control plane. If you go to the next slide, slide 19. Slide 19 is sort of the software-defined networking way of doing things, where you have a centralized controller, and the controller would be a PC running controller software, and instead of the switch populating the table that controls its behavior, this controller would be populating that table that controls the switch's behavior. So the features that the switch has really become software running on the controller, not firmware running on the switch. And it is the OpenFlow protocol that the controller uses to communicate how to update that table to the switch. And OpenFlow is kind of both a protocol and an API, so it defines the abstractions that are exposed to the software that then the switch must implement. Slide 20 shows that in a network you have typically one controller. Now, you might not physically have one controller. You might have a set of things that look like one controller, but conceptually in a network you have a single OpenFlow controller, and all of the switches in the network communicate with that controller, and that controller populates the tables in those switches that causes them to have a particular forwarding behavior. You go to slide 21. So OpenFlow exposes this abstraction called a flow table, and that flow table has different columns. One column is something called the header fields. These are things that will identify a packet to which you want to perform some action. And the header fields, I'm sorry, Tony, are you saying something?
Nope.
Okay. Slide 21, header fields. These are the things that you can match on. So remember, the controller populates this table in the switch. This table is an abstract table that the OpenFlow spec defines. The switch may not have the table that looks exactly like this, but the switch has to figure out how to translate this abstract table that you're populating into whatever it needs to do to perform the actions that are consistent with that abstract table. So in this abstract table, you have a column where you define things you want to match against on the packet. So as packets come in, you can define entries in the table that look at the port they came in on, can look at their Ethernet address, the VLAN ID, the IP source and destination address, the IP protocol, those kinds of things. You basically can put a rule in this flow table that says, if it came in on this port and it has this Ethernet address, then I want to do something to this packet. You also have counters that keep track of statistics for packets that match a certain flow entry. And then you have actions that you can apply to the packets that match your header fields. And the actions are generally forward, drop, or modify. And you could forward the packet to a port, all the ports. You can forward it to the controller. In other words, you can send the packet up to the OpenFlow controller. That kind of event is called a packet in. So go to the next slide, 22. This is sort of an example of what a flow table might look like. And so you might have a header field to say, you know, if the packet came in on port 2, drop the packet. You can have things that match on multiple parts of the packet. So if you look at the last two entries, the second to the last says that the ether type is an ARP, then forward to the controller. Again, that's called a packet in when you said something to a controller. And then the last entry is that if the port is 2 and the ether type is ARP, then forward normal. I'll talk about normal later on. And if you notice, the last two entries in this table might apply to the same packet. So if we had an ARP packet that came in port 2, it is both an ARP packet, and it is a packet that came in port 2 and an ARP packet. And if you have those kinds of rules in the flow table, there's a optional priority entry where you can put in the flow table a priority value that will tell the switch if you have a packet that matches more than one entry, how to resolve which entry is chosen as the matching entry. The higher number in the priority field is the one that takes precedence. So if you had a packet that came in on port 2 and was an ARP, in this sample flow table, it would be forwarded as normal. Again, there's special ports you can send packets to. The controller, you actually send the packet to the controller. Normal sends a packet to the non-OpenFlow function of the switch. So switches can have a hybrid mode, and this can be very useful. So you can have a switch where you might define a set of ports as being under OpenFlow control, and the rest of the switch behaves like it normally would. And if you, within the OpenFlow environment, send the packet to normal, you're basically punting the packet to the part of the switch that isn't under OpenFlow control. This can be really useful in a number of cases. So for example, you might have a firewall, and maybe you want to have an OpenFlow section, controlled section of that firewall, and then packets to get through there, you want to go through the normal firewall, and maybe you forward them to normal. Flood is another one that can be useful if within the context of your OpenFlow environment, there's something that makes sense for flooding, like if you defined a VLAN as being under OpenFlow control, Flood would send the packet out all the ports in that VLAN. Next slide, 24. There are also, when you install these entries in the flow table, there are timers. There are idle timeouts and hard timeouts. So when you put an entry in a flow table on the switch, you can send an idle timeout, which says if no packets match this entry in so many seconds, remove the entry. And you can also have a hard timeout that says regardless of whether packets match or not, after so many seconds, remove the entry. There are two approaches to populating these tables. One is called proactive, the other is reactive. They're not exclusive. You could do both. Examples of proactive are, in the case of the Internet 2 bandwidth on demand application, where you go to a web portal and provision a point-to-point path. Those rules are put in before the traffic is on the network, and those are proactive. In reactive mode, you basically, the switch is told if a packet comes in and it doesn't match any rule on the table, send the packet to the controller. And then typically what happens is the controller will then insert a new rule in the switch and send the packet back to the switch for processing. And so that way the switch is essentially dynamically being configured by the controller, and that dynamic provisioning is driven by the kinds of traffic coming into the switch. Next slide, 26. The communications between the controller and the switch. There is, in the normal communications, a switch connects to the controller, connects via TCP. Most switches allow you to also have them listen for a TCP connection, and this gets important, and we'll do this in the exercises. So you might have a switch you've configured to talk to a controller, but you've also configured a port on that switch to listen for a connection, and that could be used for debugging. So the switch talks to the controller and maybe use command line utilities to talk directly to the switch. And so you can verify what's really happening in the switch. I'm going to give you a quick example of how something like topology discovery can take place in an OpenFlow environment. So you have have a bunch of switches, maybe you randomly interconnect them, and they're all configured to talk to an OpenFlow controller. So the switches will start up. When they start up, they won't be forwarding any packets. They'll connect to the controller, and then the controller will put rules in the switches. So an example of how the controller might discover how the switches are completely interconnected. Go to slide 28. Again, each switch, you give it its basic IP information, and you point it to an OpenFlow controller. On initial connection from the switch to the controller will discover certain basic things about the switch, like how many ports it has and that kind of stuff. Go to slide 29. So to discover topology, the switch would do something like this. It would proactively place a rule in each switch, and the rule would look something like this. It could say, if the ether type looks like an LLDP packet, then send that packet to the controller. In other words, then the controller would generate LLDP packets, probably a unique one for every port it knew about on this new switch. And the controller would send that packet to the switch. And it would say, send this packet out port 1, send this packet out port 2, send this packet out port 3, each one a unique LLDP packet. And then the controller would listen for some other switch to send it that packet back, because every switch would have a rule saying if you see an LLDP packet, send it back to the controller. So if the controller can insert a packet in one switch on a specific port, and it sees that packet return on a certain port from another switch, it can learn how the switches are interconnected. And so this is a basic example of how something like topology is discovered in an OpenFlow environment. So next slide, 30. So I'm going to talk about the differences between OpenFlow 1.0 and 1.1 and forward. Slide 31. In 1.0, there's a single flow table. And the important parts of the flow table are the header fields, where you can match on certain items, and really the actions. If something matches something in the header fields, then what do you do? Starting in 1.1, they actually changed the name of the fields. They call that matching fields. Instead of actions, they have instructions, and they also have multiple tables. And they have this new concept of the way I think about it is there's this data structure that gets associated with the packet as it's going through a 1.1 switch. And so packet comes into the switch, and there's some metadata on the front of it, and then you can think of on the back of it, there's something called an action set. So the first thing it does when this packet comes in is the switch compares its header fields or match fields to entries in table 0. Remember I said it can have in OpenFlow 1.1, you can have multiple tables. So it starts out with table 0, and if the packet matches an entry in table 0, then the instructions associated with that entry will be applied to the packet. And those instructions can be like the old version actions, where it might just say drop this packet or output this packet to a certain port, or they can set things in this piece of data that's now following the packet around in the switch to do things later. So it could say, okay, I want to rewrite some part of the header. Maybe I want to change the IP address of this packet, and I'll put that in the action set. And there may be other things in the action set, and they won't be applied until I'm ready to send the packet somewhere. So completely different. They also added another kind of table called a group table. And a group table in 1.1 essentially allows you to have some indirection. So you can, one of the instructions, when you match a packet, an instruction can say go to a particular group table entry. So you can have a bunch of different flow table entries matching different kinds of packets, but all pointing to a common group table entry. And those group table entries can contain a set of other instructions to apply to the packet. They can also be used to do things like support load balance bonded links.
What slide are we on?
You know, I spoke past some slides, so let's go to slide 33. So just to reinforce, you know, in 1.1, there are instructions, and those instructions can have immediate actions, or they may set actions in the action set. Instructions can also say jump to another table, and it can only jump to tables at a higher number, so you can have something looping. Slide 34. Again, in 1.1, you get a multiple flow tables and a group table. 35, group table entries have 4 different types. So if something points to a group table, one type is all. In other words, the group table could have a set of instructions, and all of them would be applied to the packet. You could have group table types that support things like fast failover. So it could have multiple actions, but one would be designated as the active bucket of actions, which would be set externally by some process monitoring which links were live. 36. Okay, OpenFlow, QoS. Just by the way, I think we'll be able to jump into the hands-on stuff after the break. So well, wait a second. What time is it there?
There's 12 more minutes till the break.
Okay, yep. So we'll get through this and then start the hands-on stuff right after the break. Okay. OpenFlow QoS, slide 36. In the original OpenFlow 1.0 specification, there was an action called enqueue. So outside of OpenFlow, you might define multiple queues per port in a particular forwarding behavior to implement some QoS that you wanted. In OpenFlow 1.0, they did have the ability not just to forward to a port, but actually to enqueue a packet to a queue associated with a port. And you could rewrite some header fields in 1.1 that might result in future devices treating the packets differently. Slide 37. Starting in OpenFlow 1.3, they added another table. So now you have flow tables, you have the group table, and now you have this new table called the meter table. And the meter table allows you to identify meter bands for flows that point to a particular meter identifier. So go to slide 38. So you might have an entry in a flow table that has some match fields. So maybe those match fields say if the VLAN ID is this value, then apply these instructions. And one instruction might be associate this flow with a particular meter table identifier. And in that meter table identifier, there would be meter table bands. You can think of the bands as thresholds. And so and you can define them by packets per second or bytes per second. And each meter band has a type. The types are drop or remark the diffserv code point. So above a threshold, you can say, and you can have multiple thresholds, but above a threshold, you can say, above this, remark the DHCP to this value, or you could say drop it. 39 just gives the language that describes which meter band is chosen. So essentially, you can have a whole bunch of different flow entries pointing to one meter band or one meter identifier. And so all of the traffic that matches those flow entries in aggregate is evaluated for that meter identifier. And if packets appear above a certain threshold, they could be dropped or remarked. Okay, so let's jump to slide. let's jump to slide 45. So I just want to give you an idea of what the actual configuration will look like. So this slide is the configuration from a real simple HP switch, and HP switches support something called hybrid mode. And as I said before, that means some resources in the switch behave like they normally would in the switch, and other resources are actually under OpenFlow control. HP does it by VLAN. So if you look at the VLAN 10 stanza in this configuration, it just names the VLAN, it identifies which ports belong to that VLAN, and that's about it. And then if you look in the OpenFlow stanza, it says, okay, that VLAN that you defined, we're going to enable OpenFlow, which means the ports that are in that VLAN will just stop forwarding anything. Unless you put a rule in the switch, nothing will happen if a packet comes in on one of them. And you need to tell the switch where to connect to the controller that's going to populate the table, this abstract flow table in the switch, to cause it to forward packets a certain way. So it can be that simple to set up part of a switch as supporting OpenFlow. In hybrid mode and using things like HP switches, if you want to play around with OpenFlow, is a real convenient way to play around with it. Okay, slide 46 is we start the hands-on exercises, and it's just a review of what the table looked like, and how things work. Basically, we're doing the exercises are going to be using 1.0, and this abstract table is going to have the header fields, the counters, actions, priorities. Let's go to 47. As you may recall, I said switches connect to controllers, but you can usually set up a listening port on the switch, and you usually, and over both connections, OpenFlow is the protocol on both connections. And this kind of setup, you use switch connects to the controller, and then you can use some command line utilities to take a look at the OpenFlow state of the switch. This is useful for debugging. Okay. Starting at 48, we're actually going to set up the environment that we're going to use for the hands-on. So let's do this, since we're 5 minutes from the break anyway, and I need to get some water. Why don't we, everyone who wants to participate in the exercises needs to point their browser to that address, which is earlier in the slide deck, and you'll like, let's see.
It's, I think, 6.
Slide 6.
Yeah.
And you replace the X with the row number in the spreadsheet, the roster spreadsheet. Now, if you want to SSH in, if you have an X server running on your laptop, you may find that more comfortable. Some of the things we're going to be doing are going to be in terminal windows, and you can SSH in from there. In the terminal windows, SSH are probably going to be a little more responsive than the terminal windows already open on the desktop. So if I were doing the hands-on, I would probably SSH in twice and get 2 terminal windows into your VM, as well as pointing your browser at the VM. And I would use the browser to look at things like Wireshark, and I would use the terminal windows to do the things to set up the Mininet environment. So the addresses for those are on 6, and when we come back, we are going to start at slide 48.
Okay. And let's see, the agenda tells me that we resume at 11 local time. So that's a little over a half hour.
Is there anything you guys want me to do differently? You know, is there any feedback? This feels really awkward talking to my computer for hours. Make sure that.
Laughter.
Okay,
So
good.
I think, yeah, I don't know if there are any questions just quickly before the break or quick feedback. What I'm going to do is, Stephen, I'm going to reboot this, the laptop that's running Skype, to see if I can get the display back in control, and we'll resume at 11 Central Time.
Sounds good. Talk to you guys then. So I'm going to hang up and put my earpiece on the charger.
Okay, cool.
Okay, bye.
Thanks.